Hi everyone, this is the final video for week 11. We're discussing Stokes' theorem. We haven't quite proven it yet, but what we're building up to, putting all the pieces together to discuss, is that when we integrate a k-form phi over a k-dimensional boundary of a piece x of a k plus one-dimensional manifold, what we have the option of doing instead of that is to integrate the exterior derivative of phi over the manifold itself. Now, the equality is the important part, that you have a choice. You can either integrate phi over the boundary or d phi over the manifold. But what's important to discuss here is that specific dimensional instances of this theorem have been known for a really long time, like since the 1800s. Usually they're all expressed in terms of vector fields. They don't use differential forms to explain them, and in fact they were discovered before differential forms became an instrument or a tool that people use to study this particular area. So instead of evaluating a form field on an anchored parallelogram, what instead was happening was you would implement a dot product with either a unit tangent vector, like if you were doing a line integral, or like computing a work form, for instance, or a unit normal vector. That would be if you were looking for a flux form through evaluating a flux form over a surface. That's when you're dealing with a unit normal. And the direction depends on the orientation of the region of integration. And here are 4 classical theorems that you've definitely heard of that are all really Stokes' theorem, just in different dimensional settings. First, there's the fundamental theorem of line integrals. X is an oriented path in R3. It can also be R2. It can really be any setting. Its oriented boundary is 2 points, the end point B with a positive sign, the beginning A with a negative sign. And what we're seeing here is that we have an option of integrating the gradient of phi dotted with a tangent vector to this path over the entire path, or we can trade in just evaluating phi at the end point minus evaluating phi at the beginning point. Now, Green's theorem in the plane, let's scroll down a bit. What we have is a bounded region in R2, that's x, and then the boundary of that is a curve C. And so we have a choice here. We can either compute f dx plus g dy over the boundary, or we can do the partial derivative of g with respect to x minus the partial derivative of f with respect to y, and do that over the entire interior. This ends up being a notion of two-dimensional curl through the interior region. Stokes' theorem in physics, x is now a surface. Remember, in Green's theorem, it is a bounded region, but in Stokes' theorem in physics, x is a surface, and then C is an oriented boundary of that surface. And so you can choose between integrating the curl over the surface or doing a line integral of a vector field over the boundary. And last but not least, the divergence theorem. And there's a slight typo here. This should say x is a region in R3, and the surface S is the boundary of x. That's its oriented boundary. So you can think of x as like an egg with the whites and the yolks and everything, and S is like the shell. So you have a choice here between evaluating either the surface integral, right, of the vector field f through the surface, or you can compute the divergence of f through the entire solid, through the whole egg. So either taking the flux of f through the egg shell or the divergence of f through the entire egg. We're going to get into more and more of these examples. We're also going to move up towards proving Stokes' theorem lightly, but getting some experience with each of these and realizing that they are very similar in nature to Stokes' theorem, which we will talk about next week, is a key and critical result of Math 23B and math in general. That's it for now. Email me if you have any questions.